Logic, from the Greek logos, has two meanings. First, it describes the use of valid reasoning in some activity. Second, it names the normative study of reasoning, or a branch thereof. In the latter sense, it features most prominently in the subjects of philosophy, mathematics, and computer science. Logic was studied in several ancient civilizations, including India, China, Persia, and Greece. In the West, logic was established as a formal discipline by Aristotle, who gave it a fundamental place in philosophy. The study of logic was part of the classical trivium, which also included grammar and rhetoric. Logic was further extended by Al-Farabi, who categorized it into two separate groups, idea and proof. Later, Avicenna revived the study of logic and developed relationship between temporalis and the implication. In the East, logic was developed by Buddhists and Jains. Logic is often divided into three parts: inductive reasoning, abductive reasoning, and deductive reasoning. The study of logic. Upon this first, and in one sense this sole, rule of reason, that in order to learn you must desire to learn, and in so desiring not be satisfied with what you already incline to think, there follows one corollary which itself deserves to be inscribed upon every wall of the city of philosophy: do not block the way of inquiry. Charles Sanders Peirce, First Rule of Logic. The concept of logical form is central to logic, it being held that the validity of an argument is determined by its logical form, not by its content. Traditional Aristotelian syllogistic logic and modern symbolic logic are examples of formal logics. Informal logic is the study of natural language arguments. The study of fallacies is an especially important branch of informal logic. The dialogues of Plato are good examples of informal logic. Formal logic is the study of inference with purely formal content. An inference possesses a purely formal content if it can be expressed as a particular application of a wholly abstract rule, that is, a rule that is not about any particular thing or property. The works of Aristotle contain the earliest known formal study of logic. Modern formal logic follows and expands on Aristotle. In many definitions of logic, logical inference and inference with purely formal content are the same. This does not render the notion of informal logic vacuous, because no formal logic captures all of the nuance of natural language. Symbolic logic is the study of symbolic abstractions that capture the formal features of logical inference. Symbolic logic is often divided into two branches: propositional logic and predicate logic. Mathematical logic is an extension of symbolic logic into other areas, in particular to the study of model theory, proof theory, set theory, and recursion theory. Logical form. Logic is generally considered formal when it analyzes and represents the form of any valid argument type. The form of an argument is displayed by representing its sentences in the formal grammar and symbolism of a logical language to make its content usable in formal inference. If one considers the notion of form too philosophically loaded, one could say that formalizing simply means translating English sentences into the language of logic. This is called showing the logical form of the argument. It is necessary because indicative sentences of ordinary language show a considerable variety of form and complexity that makes their use in inference impractical. It requires, first, ignoring those grammatical features irrelevant to logic, such as gender and declension, if the argument is in Latin, replacing conjunctions irrelevant to logic, such as but with logical conjunctions, like and replacing ambiguous or alternative logical expressions, any, every, etc., with expressions of a standard type, such as all, or the universal quantifier. Second, certain parts of the sentence must be replaced with schematic letters. Thus, for example, the expression all as RBS shows the logical form common to the sentences all men are mortals, all cats are carnivores, all Greeks are philosophers, and so on. That the concept of form is fundamental to logic was already recognized in ancient times. Aristotle uses variable letters to represent valid inferences in prior analytics, leading Jan Lukasiewicz to say that the introduction of variables was one of Aristotle's greatest inventions. According to the followers of Aristotle, such as Ammonius, only the logical principles stated in schematic terms belong to logic, not those given in concrete terms. The concrete terms man, mortal, etc., are analogous to the substitution values of the schematic placeholders ABC, which were called the matter Greekile of the inference. The fundamental difference between modern formal logic and traditional or Aristotelian logic lies in their differing analysis of the logical form of the sentences they treat. In the traditional view, the form of the sentence consists of 1. A subject, e.g., man, plus a sign of quantity, all, or some, or no. 2. The copula, which is of the form is, or is not. 3. A predicate, e.g., mortal. Thus, all men are mortal. The logical constants such as all, no, and so on, plus sentential connectives such as and, or, were called syncagogrammatic terms, from the Greek kategore, to predicate, and sign, together with. This is a fixed scheme, where each judgment has an identified quantity and copula, determining the logical form of the sentence. According to the modern view, the fundamental form of a simple sentence is given by a recursive scheme, involving logical connectives such as a quantifier with its bound variable, which are jointed by juxtaposition to other sentences, which in turn may have logical structure. The modern view is more complex, since a single judgment of Aristotle's system involves 2 or more logical connectives. For example, the sentence all men are mortal involves, in term logic, 2 non-logical terms: is a man here M, and is mortal here D. The sentence is given by the judgment A, M, D. In predicate logic, the sentence involves the same 2 non-logical concepts, here analyzed as and the sentence is given by, involving the logical connectives for a universal quantification and implication. But equally, the modern view is more powerful. Medieval logicians recognized the problem of multiple generality, where Aristotelian logic is unable to satisfactorily render such sentences as some guys have all the lug, because both quantities all and some may be relevant in an inference, but the fixed scheme that Aristotle used allows only one to govern the inference. Just as linguists recognize recursive structure in natural languages, it appears that logic needs recursive structure. Deductive and inductive reasoning, and retroductive inference. Deductive reasoning concerns what follows necessarily from given premises, if A, then B. However, inductive reasoning, the process of deriving a reliable generalization from observations, has sometimes been included in the study of logic. Similarly, it is important to distinguish deductive validity and inductive validity, called cogency. An inference is deductively valid if and only if there is no possible situation in which all the premises are true, but the conclusion false. An inductive argument can be neither valid nor invalid; its premises give only some degree of probability, but not certainty, to its conclusion. The notion of deductive validity can be rigorously stated for systems of formal logic in terms of the well-understood notions of semantics. Inductive validity, on the other hand, requires us to define a reliable generalization of some set of observations. The task of providing this definition may be approached in various ways, some less formal than others. Some of these definitions may use mathematical models of probability. For the most part, this discussion of logic deals only with deductive logic. Retroductive inference is a mode of reasoning that Peirce proposed as operating over and above induction and deduction to open up new ground in processes of theorizing. 1911, page 2. He defines retroduction as a logical inference that allows us to render comprehensible some observations/events we perceive by relating these back to a posited state of affairs that would help to shed light on the observations. Peirce, 1911, page 2. He remarks that the characteristic formula of reasoning that he calls retroduction is that it involves reasoning from a consequent, any observed/experienced phenomena that confront us, to an antecedent, that is, a posited state of things that helps us to render comprehensible the observed phenomenon. or, as he otherwise puts it, it can be considered as regressing from a consequent to a hypothetical antecedent. 1911, page 4. Some authors suggest that this mode of inference can be used within social theorizing to postulate social structures/mechanisms that explain the way that social outcomes arise in social life, and that in turn indicates that these structures or mechanisms are alterable with sufficient social will and envisioning of alternatives. In other words, this logic is specifically liberative in that it can be used to point to transformative potential in our way of organizing our social existence by our re-examining/exploring the deep structures that generate outcomes and life chances for people. In her book on New Racism, 2010, Norma Rahm offers an account of various interpretations of what can be said to be involved in retroduction as a form of inference, and how this can also be seen to be linked to a style of theorizing and caring, where processes of knowing, which she sees as dialogically rooted, are linked to social justice projects. Consistency, validity, soundness, and completeness. Among the important properties that logical systems can have: consistency, which means that no theorem of the system contradicts another; validity, which means that the system's rules of proof never allow a false inference from true premises. A logical system has the property of soundness when the logical system has the property of validity and uses only premises that prove true, or, in the case of axioms, are true by definition. Completeness of a logical system, which means that if a formula is true, it can be proven; if it is true, it is a theorem of the system. Soundness. The term soundness has multiple separate meanings, which creates a bit of confusion throughout the literature. Most commonly, soundness refers to logical systems, which means that if some formula can be proven in a system, then it is true in the relevant model/structure. If A is a theorem, it is true. This is the converse of completeness. A distinct, peripheral use of soundness refers to arguments, which means that the premises of a valid argument are true in the actual world. Some logical systems do not have all four properties. As an example, Kurt Gödel's incompleteness theorems show that sufficiently complex formal systems of arithmetic cannot be consistent and complete. However, first-order predicate logics not extended by specific axioms to be arithmetic formal systems with equality can be complete and consistent. Rival conceptions of logic. Logic arose, see below, from a concern with correctness of argumentation. Modern logicians usually wish to ensure that logic studies just those arguments that arise from appropriately general forms of inference. For example, Thomas Hofweber writes in the Stanford Encyclopedia of Philosophy that logic does not, however, cover good reasoning as a whole. That is the job of the theory of rationality. Rather, it deals with inferences, whose validity can be traced back to the formal features of the representations that are involved in that inference, be they linguistic, mental, or other representations. By contrast, Immanuel Kant argued that logic should be conceived as the science of judgment, an idea taken up in Gottlob Frege's logical and philosophical work. But Frege's work is ambiguous in the sense that it is both concerned with the laws of thought as well as with the laws of truth, i.e. it both treats logic in the context of the theory of the mind and treats logic as the study of abstract formal structures. History. Aristotle, 384–322 BC. In Europe, logic was first developed by Aristotle. Aristotelian logic became widely accepted in science and mathematics, and remained in wide use in the West until the early 19th century. Aristotle's system of logic was responsible for the introduction of hypothetical syllogism, temporal modal logic, and inductive logic, as well as influential terms such as terms, predicables, syllogisms, and propositions. In Europe during the later medieval period, major efforts were made to show that Aristotle's ideas were compatible with Christian faith. During the High Middle Ages, logic became a main focus of philosophers who would engage in critical logical analyses of philosophical arguments, often using variations of the methodology of scholasticism. In 1323, William of Ockham's influential science.Logic was released. By the 18th century, the structured approach to arguments had degenerated and fallen out of favor, as depicted in Holberg's satirical play Erasmus Montanus. The Chinese logical philosopher Gong Sunlong, ca. 325–250 BC, proposed the paradox 1 and 1 cannot become 2, since neither becomes 2. In China, the tradition of scholarly investigation into logic, however, was repressed by the Qin dynasty following the legalist philosophy of Hamfizi. In India, innovations in the scholastic school, called Nyaya, continued from ancient times into the early 18th century with the Navya school. By the 16th century, it developed theories resembling modern logic, such as Al-Farabi's distinction between sense and reference of proper names, and his definition of number, as well as the theory of restrictive conditions for universals, anticipating some of the developments in modern set theory. Since 1824, Indian logic attracted the attention of many Western scholars and has had an influence on important 19th-century logicians such as Charles Babbage, Augustus De Morgan, and George Boole. In the 20th century, Western philosophers like Stanislaw Schaer and Klaus Glashoff have explored Indian logic more extensively. The syllogistic logic developed by Aristotle predominated in the West until the mid-19th century, when interest in the foundations of mathematics stimulated the development of symbolic logic, now called mathematical logic. In 1854, George Boole published an investigation of the laws of thought on which are founded the mathematical theories of logic and probabilities, introducing symbolic logic and the principles of what is now known as Boolean logic. In 1879, Al-Farabi published Begriffsschrift, which inaugurated modern logic with the invention of quantifier notation. From 1910 to 1913, Alfred North Whitehead and Bertrand Russell published Principia Mathematica on the foundations of mathematics, attempting to derive mathematical truths from axioms and inference rules in symbolic logic. In 1931, Gödel raised serious problems with the foundationalist program, and logic ceased to focus on such issues. The development of logic since Frege, Russell, and Wittgenstein had a profound influence on the practice of philosophy and the perceived nature of philosophical problems. See analytic philosophy and philosophy of mathematics. Logic, especially sentential logic, is implemented in computer logic circuits and is fundamental to computer science. Logic is commonly taught by university philosophy departments, often as a compulsory discipline. Topics in logic. Syllogistic logic. The Organon was Aristotle's body of work on logic, with the prior analytics constituting the first explicit work in formal logic, introducing the syllogistic. The parts of syllogistic logic, also known by the name term logic, are the analysis of the judgments in two propositions consisting of two terms that are related by one of a fixed number of relations, and the expression of inferences by means of syllogisms that consist of two propositions sharing a common term as premise, and a conclusion, that is a proposition involving the two unrelated terms from the premises. Aristotle's work was regarded in classical times, and from medieval times in Europe and the Middle East, as the very picture of a fully worked-out system. However, it was not alone. The Stoics proposed a system of propositional logic that was studied by medieval logicians. Also, the problem of multiple generality was recognized in medieval times. Nonetheless, problems with syllogistic logic were not seen as being in need of revolutionary solutions. Today, some academics claim that Aristotle's system is generally seen as having little more than historical value, though there is some current interest in extending term logics, regarded as made obsolete by the advent of propositional logic and the predicate calculus. Others use Aristotelian argumentation theory to help develop and critically question argumentation schemes that are used in artificial intelligence and legal arguments. Propositional logic, sentential logic. Propositional calculus. A propositional calculus or logic, also a sentential calculus, is a formal system in which formulae representing propositions can be formed by combining atomic propositions using logical connectives, and in which a system of formal proof rules establishes certain formulae as theorems. Predicate logic. Predicate logic is the generic term for symbolic formal systems such as first-order logic, second-order logic, many-sorted logic, and infinitary logic. Predicate logic provides an account of quantifiers general enough to express a wide set of arguments occurring in natural language. Aristotelian syllogistic logic specifies a small number of forms that the relevant part of the involved judgments may take. Predicate logic allows sentences to be analyzed into subject and argument in several additional ways, allowing predicate logic to solve the problem of multiple generality that had perplexed medieval logicians. The development of predicate logic is usually attributed to Gottlob Frege, who is also credited as one of the founders of analytical philosophy, but the formulation of predicate logic most often used today is the first-order logic presented in Principles of Mathematical Logic by David Hilbert and Wilhelm Ackermann in 1928. The analytical generality of predicate logic allowed the formalization of mathematics, drove the investigation of set theory, and allowed the development of Alfred Tarski's approach to model theory. It provides the foundation of modern mathematical logic. Frege's original system of predicate logic was second-order rather than first-order. Second-order logic is most prominently defended against the criticism of Willard Van Orman Quine and others by George Bullis and Stuart Shapiro. Modal logic. In languages, modality deals with the phenomenon that subparts of a sentence may have their semantics modified by special verbs or modal particles. For example, we go to the games can be modified to give we should go to the games, and we can go to the games, and perhaps we will go to the games. More abstractly, we might say that modality affects the circumstances in which we take an assertion to be satisfied. Aristotle's logic is in large parts concerned with the theory of non-modalized logic. Although there are passages in his work, such as the famous sea battle argument in De Interpretatio 9, that are now seen as anticipations of modal logic and its connection with potentiality and time. The earliest formal system of modal logic was developed by Avicenna, whom ultimately developed a theory of temporally modalized syllogistic. While the study of necessity and possibility remained important to philosophers, little logical innovation happened until the landmark investigations of Clarence Irving Lewis in 1918, who formulated a family of rival axiomatizations of the alethic modalities. His work unleashed a torrent of new work on the topic, expanding the kinds of modality treated to include deontic logic and epistemic logic. The seminal work of Arthur Prior applied the same formal language to treat temporal logic and paved the way for the marriage of the two subjects. Saul Kripke discovered, contemporaneously with rivals, his theory of frame semantics, which revolutionized the formal technology available to modal logicians and gave a new graph-theoretic way of looking at modality that has driven many applications in computational linguistics and computer science, such as dynamic logic. Informal reasoning. The motivation for the study of logic in ancient times was clear. It is so that one may learn to distinguish good from bad arguments, and so become more effective in argument and oratory, and perhaps also to become a better person. Half of the works of Aristotle's Organon treat inference as it occurs in an informal setting, side by side with the development of the syllogistic, and in the Aristotelian school, these informal works on logic were seen as complementary to Aristotle's treatment of rhetoric. This ancient motivation is still alive, although it no longer takes center stage in the picture of logic. Typically, dialectical logic forms the heart of a course in critical thinking, a compulsory course at many universities. Argumentation theory is the study and research of informal logic, fallacies, and critical questions as they relate to everyday and practical situations. Specific types of dialogue can be analyzed and questioned to reveal premises, conclusions, and fallacies. Argumentation theory is now applied in artificial intelligence and law. Mathematical logic. Mathematical logic really refers to two distinct areas of research. The first is the application of the techniques of formal logic to mathematics and mathematical reasoning. And the second, in the other direction, the application of mathematical techniques to the representation and analysis of formal logic. The earliest use of mathematics and geometry in relation to logic and philosophy goes back to the ancient Greeks such as Euclid, Plato, and Aristotle. Many other ancient and medieval philosophers applied mathematical ideas and methods to their philosophical claims. Kurt Gödel. One of the boldest attempts to apply logic to mathematics was undoubtedly the logicism pioneered by philosopher-logicians such as Gottlob Frege and Bertrand Russell. The idea was that mathematical theories were logical tautologies, and the program was to show this by means to a reduction of mathematics to logic. The various attempts to carry this out met with a series of failures, from the crippling of Frege's project and his Grundgesetze by Russell's paradox, to the defeat of Hilbert's program by Gödel's incompleteness theorems. Both the statement of Hilbert's program and its refutation by Gödel depended upon their work establishing the second area of mathematical logic, the application of mathematics to logic in the form of proof theory. Despite the negative nature of the incompleteness theorems, Gödel's completeness theorem, a result in model theory, and another application of mathematics to logic, can be understood as showing how close logicism came to being true. Every rigorously defined mathematical theory can be exactly captured by a first-order logical theory. Frege's proof calculus is enough to describe the whole of mathematics, though not equivalent to it. Thus we see how complementary the two areas of mathematical logic have been. If proof theory and model theory have been the foundation of mathematical logic, they have been but two of the four pillars of the subject. Set theory originated in the study of the infinite by George Cantor, and it has been the source of many of the most challenging and important issues in mathematical logic, from Cantor's theorem, through the status of the axiom of choice, and the question of the independence of the continuum hypothesis, to the modern debate on large cardinal axioms. Recursion theory captures the idea of computation in logical and arithmetic terms. Its most classical achievements are the undecidability of the Entscheidungsproblem by Alan Turing, and his presentation of the Church-Turing thesis. Today recursion theory is mostly concerned with the more refined problem of complexity classes, when is a problem efficiently solvable, and the classification of degrees of unsolvability. Philosophical logic. Philosophical logic deals with formal descriptions of natural language. Most philosophers assume that the bulk of normal proper reasoning can be captured by logic, if one can find the right method for translating ordinary language into that logic. Philosophical logic is essentially a continuation of the traditional discipline that was called logic before the invention of mathematical logic. Philosophical logic has a much greater concern with the connection between natural language and logic. As a result, philosophical logicians have contributed a great deal to the development of non-standard logics, e.g., free logics, tense logics, as well as various extensions of classical logic, e.g., modal logics, and non-standard semantics for such logics, e.g., Kripke's technique of supervaluations in the semantics of logic. Logic and the philosophy of language are closely related. Philosophy of language has to do with the study of how our language engages and interacts with our thinking. Logic has an immediate impact on other areas of study. Studying logic and the relationship between logic and ordinary speech can help a person better structure his own arguments and critique the arguments of others. Many popular arguments are filled with errors because so many people are untrained in logic and unaware of how to formulate an argument correctly. Computational logic. Logic cut to the heart of computer science as it emerged as a discipline. Alan Turing's work on the Entscheidungsproblem followed from Kurt Gödel's work on the incompleteness theorems, and the notion of general-purpose computers that came from this work was of fundamental importance to the designers of the computer machinery in the 1940s. In the 1950s and 1960s, researchers predicted that when human knowledge could be expressed using logic with mathematical notation, it would be possible to create a machine that reasons, or artificial intelligence. This was more difficult than expected because of the complexity of human reasoning. In logic programming, a program consists of a set of axioms and rules. Logic programming systems such as Prolog compute the consequences of the axioms and rules in order to answer a query. Today, logic is extensively applied in the fields of artificial intelligence and computer science, and these fields provide a rich source of problems in formal and informal logic. Argumentation theory is one good example of how logic is being applied to artificial intelligence. The ACM computing classification system, in particular, regards Section F.3 on logics and meanings of programs and F.4 on mathematical logic and formal languages as part of the theory of computer science. This work covers formal semantics of programming languages as well as work of formal methods such as Hoare logic. Boolean logic as fundamental to computer hardware, particularly the system section B.2 on arithmetic and logic structures relating to operatives and not, and, or. Many fundamental logical formalisms are essential to section I.2 on artificial intelligence, for example modal logic and default logic and knowledge representation formalisms and methods, horn clauses in logic programming, and description logic. Furthermore, computers can be used as tools for logicians. For example, in symbolic logic and mathematical logic, proofs by humans can be computer-assisted. Using automated theorem proving, the machines can find and check proofs as well as work with proofs too lengthy to write out by hand. Bivalence and the law of the excluded middle. The logics discussed above are all bivalent, or two-valued, that is, they are most naturally understood as dividing propositions into true and false propositions. Non-classical logics are those systems that reject bivalence. Hegel developed his own dialectic logic that extended Kant's transcendental logic, but also brought it back to ground by assuring us that neither in heaven nor in earth, neither in the world of mind nor of nature, is there anywhere such an abstract either or, as the understanding maintains. Whatever exists is concrete, with difference and opposition in itself. In 1910, Nikolai Vasilyev extended the law of excluded middle and the law of contradiction, and proposed the law of excluded fourth and logic tolerant to contradiction. In the early 20th century, Jan Lukasiewicz investigated the extension of the traditional true/false values to include a third value, possible, so inventing ternary logic, the first multi-valued logic. Logic such as fuzzy logic have since been devised with an infinite number of degrees of truth represented by a real number between 0 and 1. Intuitionistic logic was proposed by L. J. Brouwer as the correct logic for reasoning about mathematics, based upon his rejection of the law of the excluded middle as part of his intuitionism. Brouwer rejected formalization in mathematics, but his student Arend Hating studied intuitionistic logic formally, as did Gerhard Gentzen. Intuitionistic logic is of great interest to computer scientists, as it is a constructive logic and can be applied for extracting verified programs from proofs. Modal logic is not truth conditional, and so it has often been proposed as a non-classical logic. However, modal logic is normally formalized with the principle of the excluded middle, and its relational semantics is bivalent, so this inclusion is disputable. Is logic empirical? What is the epistemological status of the laws of logic? What sort of argument is appropriate for criticizing purported principles of logic? In an influential paper entitled Is Logic Empirical? Hilary Putnam, building on a suggestion of W. V. Quine, argued that in general the facts of propositional logic have a similar epistemological status as facts about the physical universe, for example, as the laws of mechanics, or of general relativity, and in particular that what physicists have learned about quantum mechanics provides a compelling case for abandoning certain familiar principles of classical logic. If we want to be realist about the physical phenomena described by quantum theory, then we should abandon the principle of distributivity. substituting for classical logic the quantum logic proposed by Gerrit Birkhoff and John von Neumann. Another paper of the same name by Sir Michael Dummett argues that Putnam's desire for realism mandates the law of distributivity. Distributivity of logic is essential for the realist's understanding of how propositions are true of the world in just the same way as he has argued the principle of bivalence is. In this way, the question, is logic empirical? Can be seen to lead naturally into the fundamental controversy in metaphysics on realism versus anti-realism. Implication, strict or material. It is obvious that the notion of implication formalized in classical logic does not comfortably translate into natural language by means of it, and due to a number of problems called the paradoxes of material implication. The first class of paradoxes involves counterfactuals, such as if the moon is made of green cheese, then 2 + 2 = 5, which are puzzling because natural language does not support the principle of explosion. Eliminating this class of paradox was the reason for C.I. Lewis's formulation of strict implication, which eventually led to more radically revisionist logic such as relevance logic. The second class of paradoxes involves redundant premises, falsely suggesting that we know the succedent because of the antecedent. Thus, if that man gets elected, Granny will die is materially true since Granny is mortal, regardless of the man's election prospects. Such sentences violate the Gricean maxim of relevance and can be modeled by logics that reject the principle of monotonicity of entailment, such as relevance logic. Tolerating the impossible. Hegel was deeply critical of any simplified notion of the law of non-contradiction. It was based on Leibniz's idea that this law of logic also requires a sufficient ground to specify from what point of view, or time, one says that something cannot contradict itself. A building, for example, both moves and does not move. The ground for the first is our solar system, and for the second the Earth. In Hegelian dialectic, the law of non-contradiction, of identity, itself relies upon difference, and so is not independently assertable. Closely related to questions arising from the paradoxes of implication comes the suggestion that logic ought to tolerate inconsistency. Relevance logic and paraconsistent logic are the most important approaches here, though the concerns are different. A key consequence of classical logic, and some of its rivals, such as intuitionistic logic, is that they respect the principle of explosion, which means that the logic collapses if it is capable of deriving a contradiction. Graham Priest, the main proponent of dialetheism, has argued for paraconsistency on the grounds that there are in fact true contradictions. Rejection of logical truth. The philosophical vein of various kinds of skepticism contains many kinds of doubt and rejection of the various bases on which logic rests, such as the idea of logical form, correct inference, or meaning, typically leading to the conclusion that there are no logical truths. Observe that this is opposite to the usual views in philosophical skepticism, where logic directs skeptical enquiry to doubt received wisdoms, as in the work of Sextus Empiricus. Friedrich Nietzsche provides a strong example of the rejection of the usual basis of logic. His radical rejection of idealization led him to reject truth as a mobile army of metaphors, metonyms, and anthropomorphisms, in short, metaphors which are worn out and without sensuous power, coins which have lost their pictures, and now matter only as metal, no longer as coins. His rejection of truth did not lead him to reject the idea of either inference or logic completely, but rather suggested that logic came into existence in man's head, out of illogic, whose realm originally must have been immense. Innumerable beings who made inferences in a way different from ours perished. 41. Thus, there is the idea that logical inference has a use as a tool for human survival, but that its existence does not support the existence of truth, nor does it have a reality beyond the instrumental. Logic, too, also rests on assumptions that do not correspond to anything in the real world. 42. This position held by Nietzsche, however, has come under extreme scrutiny for several reasons. He fails to demonstrate the validity of his claims, and merely asserts them rhetorically. Although, since he is criticizing the established criteria of validity, this does not undermine his position, for one could argue that the demonstration of validity provided in the name of logic was just as rhetorically based. Some philosophers, such as Jürgen Habermas, claim his position is self-refuting and accuse Nietzsche of not even having a coherent perspective, let alone a theory of knowledge. 43 Again, it is unclear if this is a decisive critique, for the criteria of coherency and consistent theory are exactly what is under question. George Lukács, in his book The Destruction of Reason, asserts that, were we to study Nietzsche's statements in this area from a logico-philosophical angle, we would be confronted by a dizzy chaos of the most lurid assertions, arbitrary and violently incompatible. 44 Still, in this respect his theory would be a much better deposition of a confused and chaotic reality than any consistent and compatible theory. Bertrand Russell referred to Nietzsche's claims as empty words in his book A History of Western Philosophy. 45.